Today what we want to do is we want to discuss a new aspect in image processing which is called image compression. It's widely referred as coding, because what we try to do is we try to code our image, our streams that we have in our hand, and we try to express it as small as it is possible, because you want to take a photo with a very, nowadays we have very cool cameras with lots of megapixels, right? So you take a photo and you want to send this photo as an attachment to an email to your friend, or you want to upload it very quickly and you don't want to really spend too much time or too much money in order to upload an image, or to send it through lots of different applications. So it's very important for us to come up with an algorithm or with a logic that we can compress this huge amount of data that we have. So what we want to do today, we want to discuss about this image compression, and we want to see from which aspects or point of view we can look at these questions. So we understand what is the problem. The problem is that we have huge number of bits that needs to be transmitted. Imagine that you are taking a photo, you are taking a picture, you are taking a picture, and the picture is 1000 by 1000, right? And it is a color image, and it's an 8-bit image, let's say. We know that nowadays we have these HDR images which can be like, I don't know, 12 bits, 14 bits, but let's just stick with the 8 bits. So what happened, we have 24 million bits to transmit. So 4 million bits, right? So it's too much, because imagine that you have taken a video of your classroom and you have 100 frames inside it, and each of the frame has this type of image. So if you multiply by 100, so you will see that we will have 2.5 billion bits to just transmit if we have only 100 frames. And 100 frame is like a couple of seconds, right? Imagine that in each frame, in each second we have 30 frames, so it's like 3.4 seconds of video. So we understand that it's huge. So we know that this is not a good idea to just transmit all the image in one go. Towards the end of this course, we will talk about video processing slightly, like give an introduction to video processing. You understand that when it is video, actually the light will be much changed, and we have a much degree of freedom of manipulating things. So right now what we want to do, we want to discuss about a static image. You have one static image, you have the picture of Lena, and you want to send it, right? And we want to see that how we can compress this thing. In order to do in order to do the image compression, we need to go over a few definitions. I am so sure that especially if you have taken the first ICT course in high school or in university, there are two terms that they're always referring to: data and information. What is the difference between data and information?
Data is a raw, but information.
Information is a processed data. Information is processed data. So what is important for us? The important thing for us is the information, because information is something that brings you the knowledge, gives you the information, right? So knowing that from the information is extracted from data, we also understand that not all the data results into the information, or maybe several of the data will result into the same information, right? So this means that if lots of data will as a result gives us the same information, then we have something which is called data redundancy. In other words, we have lots of data which we don't really need to have them. In other words, especially in case of an image, when you look at an image, we have some parts which is the information, and we have lots of data redundancy. In other words, you have the picture of Lena, and it's 1000 by 1000, so you have, how much was that, 24 million bits, but you really don't need that 24 million bits. Maybe you can represent it with less number of bits. So what we want to do today, we want to discuss and find out how we can get this information. or how much of the redundancy is available in a specific image, right? So let's proceed by talking. Okay, we said that we have the data redundancy, right? And this is like university level, graduate level course. So when we say that there are lots of redundancy in this image, we have to be able to give some quantitative results also. To say that there are 90% or there are 10% of redundancy. So let's see how we are calculating redundancy. If you have a big object, right, a big cube, and you will be able to squeeze this one to 1/10 of its volume. How much redundancy do we have? Like we had a cube with 100, whatever unit you want to put for the volume, and then we squeeze it and we get 10. And that is enough for us in order to express everything. So it means that we have like 90% extra, right? 90% of redundancy. Now, how we come up with this, that 90% is, after we are compressing it, we calculate something which is called the compression ratio. After we have calculated how much we can compress, we can find out that, okay, the compression and the redundancy have opposite order. If we can compress more, if we can compress less, what happens? If I cannot compress at all, how much redundancy do I have? Zero. So in other words, I can always normalize. So like 1 is the maximum and 0 is the minimum that you can get. And then accordingly you can calculate the redundancy. How we calculate redundancy? Redundancy is in relation with reciprocal of compression, and we calculate it by 1 minus 1 over CR. Usually we represent redundancy and compression ratio as percentage. But we understand that if it is in percentage, it means it is between 0 and 1, right? Now, how we can calculate the compression ratio? We have not talked about the techniques of compression ratio. In this course, we want to talk about the techniques of compression ratio. But we have to find out how we can calculate the compression ratio. Compression ratio calculated in this form. If I need to have, let's say, 100 elements to make this one, okay, without any compression, and then I tell you that I can do some magic and I can beat this one. Instead of 100, I can do it with 60 or with 50 elements. So how much compression do I have? So what we do, we said that previously we had 100 elements, now we have 50 elements, so I have compressed it by 2, right? I have compressed it by 2. So how much redundancy do I have? 50% of redundancy I had, because it will be 1 minus 1 over 2. Now, if there is no compression, in other words, the number of elements, bits that you have in an image, and the number of bits that you have after you try to compress it is equal to each other, it means there is no redundancy. Where can I have the no redundancy? Imagine that you have an image, let's say one line, that each pixel has different value. Let's say the length is 1 by 256, so you have the value 0, 1, 2 to 255. In other words, each of them are independent from each other. You cannot say that, hey, I can ignore some. We will come to the point that you can ignore some and still you will be alright, so you can compress it. Now, before we go to the next slide and start to talk how we can compress, you have to keep it in your mind there are two general ways of doing the compression. One of the way is that I am squeezing this, but I know that if I release it, it will get back to what it is without any loss. We call it lossless compression, right? In other words, although you need to have, let's say, 2 million bits, you are representing it by maybe 1 million bits, but when you want to reconstruct it, you can get everything back without any problem. You can get everything back without any problem. A very good example will be an image like this. Imagine this is 1, this is row 500, and this is row 1000, okay? And it is all black, and this is all white, right? Look how and I said that how many bits do I need to represent it? 24 million bits. Is it true? And even, let's say that this is a black and white image. So I only need 2 million bits. Why 2?
2.
Because I need to have only,
1, 0, 2.
so I need only 1 bit, right? So I don't need even 2. I need only 1 bit in order to represent it, because it can be either 0 or 1. So I need 1 million bit. However, I can represent it also in this form, because it's a very nice thing. I can say from row 1 till row 499, I have 1. From row 500 to 1000, I have 0. Now what I need to memorize is this. Number 1 is 1 bit. 499 is how many bits? 9 bits. 500 is 9 bits, and 1000
10 bit.
10 bits, right? No, 256, 512, so I can represent this one by 9 bits, then here I need 10 bits. Now, and of course for 1 I need 1 bit, for 0 I need 1 bit. So in other words, how many bits do I need? 10, 11, 21, 31 bits. I can represent this image, and okay, I need to know that the number of columns are also 1000, because it's all unique, so I need another 10 bits. So let's say 41. So I can reconstruct this image completely without any loss by having only 41 bits. Let's say 40 bit approximately. So in this previously I had 1 million. Now I can represent it with 40. So it's 20. So how much did I compress? 25,000 times, right? Oh, 2,500 times. But we understand this is a very specific image, right? Even for this very specific image, I can compress it more. How can I compress it more? How can I compress it more? I think for me, in order to reconstruct it, I need to know number of rows, number of columns, and the row which change happens, and by change happens I can also say the bit after the change. In other words, I can by default I can tell you that you put 1, like default value is 1, bit number 1, right? So here I have 1000, which is 10 bits. I have 1000, which is 10 bits. It happens on row 500, which is 9 bits. And it changed to bit 0, so which is 1 bit. So actually, really, for this image, if I have 30 bits, I can reconstruct it completely. without any loss. So, but again, this was a very nice image. This logic, which is very simple logic, a straightforward logic, will miserably fail if I have, let's say, 5 by 5 image, 5 by 5 image, and I randomly have blacks and whites, right? Then you really cannot define a pattern. Here I could define a pattern, and I was using this pattern in order to compress it. So that logic is not helping me here. We are talking about the techniques which are very generalized. I don't care about if there is a pattern or not, and we try to compress it. Now, what I tried to say here in this example was, I am compressing a huge event for this specific image, but I can reconstruct it back. In other words, if I give you this data, and without you knowing what is the original thing, you can draw the original image back. And you can show it to someone and they can understand that this is after coding. But sometimes what happens is this. You have an image like this, and if you want to compress it without losing anything, you see that you can compress it with by compression ratio of, let's say, 3. In other words, you can compress it 3 times, right? You can compress it at like 3 times less than the number of bits that you have. And you can get the image back completely. But I tell you that, and imagine we also had this one, okay? And I tell you that, look, if you ignore this bit, if you change this one to white, I can give you another technique, if I change this one to white, which compress this one 15 times. So, you say that, okay, I mean, really I can lose that specific bit. I can lose one of my pixels, I understand. This is not exactly the same, but I'm compressing it now 15 times. So it's like a lot of time is much higher. And in the reality, this is, without loss, is like 2 times compression, or maybe 3 compression. And here we are talking about 50 times of compression. And we are not talking about the 5 by 5 image, we are talking about like 2000 by 3000 image. So you understand that 50 times will be significantly affect on your total cost, on your total results. So sometimes we lose, but we gain a lot in the compression. So we are losing a little bit, we are changing a few of the bits. Maybe you don't change it. Simply the method, when you are reconstructing it, it starts to lose some of the information, but we don't care because we are gaining a lot in the compression ratio. This type of compression is called lossy compression. So lossy compression means that when we are reconstructing, we will not get exactly the same image as the original one was. And we will talk about what type of losses are good losses. I mean, imagine that you are compressing Lena, and when you are reconstructing it, it comes without eyes. I mean, you don't want it, right? So it's very important to know what we are compressing. There are 3 ways of doing this compression: coding redundancy method, interpixel redundancy method, and psychovisual redundancy method. And we want to talk about each of them in details and see how they are working. And we start by talking about the coding redundancy method. Coding redundancy method works in this form. We are looking at the probability of appearance of the pixels when we want to do the coding. Now, let's get back much before in the first example, which I said that, you know, guys, we have an image which is 1000 by 1000, okay? And it is the picture of our classroom. and there is like sometimes Egils is sleeping, so it's with those eyes, but and different hairstyles, your stuff, your hairstyle, like right. So we have a picture like this, and it's a color image, right? And it's 1000 by 1000, and we know that we need to have 3 layers, and each layer has needs 8 bits to represent, right? So this is how we calculate. We have this. We need this to have 24 million bits. But I took this photo. And I can see that because here the majority of the people have a white skin or bright skin, so probability of have pixels which are around 200 and 200 above is high. And if I take a photo like this, there is absolutely no one who has anything green. Okay, Ulari has a little bit of green strip, but I take this photo, so there is no green. So probability of having green is 0 because there is no green, right? If there is no green, why do I need to allocate 8 bits for the green? 8 multiplied by 3. Why do I need to allocate 24 bits for the green? Then there is no green. Do you understand? And if some of the bits are more frequent, why do I need to give them a very big length? Whereas I know that they will happen more, so I can allocate them less number of bits because I will give them more importance also, right? In other words, I will say that, look Gustav, you are a very important person in the class and you are number 1. And everybody else is a 2-digit student. So you are like 10, 11, 12. So I don't need to give him 2 space. I give him 1 space for his number because he is 1 digit. Do you understand? Because he's very important. The same thing can happen in the image. There can be some of the pixels which appear a lot and a lot and a lot. So we don't give them 8-bit. We tell them that, look guy, you are very important. So you are not space in order to fill you with zeros and 1. You are very important and you have only 1 bit and it is 1. You are either there, 1, or you are not there, 0. So you understand, when you are very important, you do not need to have a 10 or 8 space to carry your number because you are number 1. So you need only 1 space to carry your bit, right? So this was the whole idea behind the coding redundancy. They said that let's calculate the probability of the pixel. Let's do not treat everything equally. Those pixels which are very important, and very important in pixels means that those pixels which are repeating a lot, we give them less number of bits because they can be like our bit number 1, they can be our bit number 2 based on their importance. So I do not need to give them 8 locations, I will give them maybe 2 locations, I will give them maybe 3 locations, okay? And now, based on that, the bits which are very, very less important, we give them maybe more than 8 space, maybe we give them 10 space. But we know that they will hardly happen. Like in case of green, we know that even if I give them 100 space, it will never happen. So there is nothing to be worried. So the coding said that, so let's allocate the location, the bit locations, like how many bits we want, for let's allocate less number of bit location for the high probable bits and give bigger location for the low probable one. Why we want to do this? Because there is something which is called the average number of bits required. And the average number of bits required is calculated in this form. All this, this way. So, how we are calculating it is this. The probability multiplied by the number of bits that we have. And till now, all the images that you had, it was an 8-bit image, right? So what was the average length? For, in other words, how many bits did we need to know in order to represent a pixel till today? 8. because it doesn't matter if it has high probability or low probability. Every pixels were very equal to each other. So it's like a communist country, right? It doesn't matter how much you work, it doesn't matter what is your work, you all get the same amount of money, right? So it was one thing like that. So we had the pixels 0, 1, 2, 3, 4, 5, 6 till 7. Let's say it was a 3-bit representation. And we gave all of them 3 bits. We gave all of them 3 bits. And when we calculate the average, because everything was 3, we get 3. Like we have 100 students, everybody get 80. What is the average? The average is 80 because everyone is equal to each other. But imagine within this example, we had different probability of occurrence. These numbers are random. We just randomly from the book we gave these numbers. It means that if I look at it, it means that pixel with the intensity value of 1 has the highest number of appearance. Has highest number of appearance. And a bit with the pixel value of 111, which is 7, has the lowest probability of appearance. So what we want to do, we want to look at these probability values and assign new number of bits. But before we do it, Egils, let's see how we calculate the probabilities. How do we calculate the probabilities, Ozan?
We check all bits and like histogram can have this.
How can it help us? That's very correct. We have to use histogram, but how can we use histogram?
Then histogram just show like in one specific bit how many times it used. So we can check how many times all bit we used, and with specific bit just we need to divide.
Yeah, exactly. Imagine if h is 2 to the power n minus 1. If h is histogram of the image, so it means that, and hi tells us how many pixels has intensity I, right? For example, for the 3 bits, h for 3 bits will be h0, h1, h2, h3, h4, h5, h6, and h7. In other words, in the reality, when you look at the numbers, it will tell you that 10, 200, 15, whatever, right? Right? And we know that if I add all these values, what do I get? Thomas, if I add all these h values, what do I get? Martin?
We'll get the number of pixels.
Yeah, total number of pixels. Like in here, it was 10,000, about 1,000 by 1,000, so I will get 1 million, right? So, if this is the histogram, then the probability is calculated as, we call P is hi divided by the summation of all hi's for I from 0 to 2 to the power n minus 1. Right? So this is the probability values. In other words, it's equal to h0 divided by the summation of hi's, h1 divided by summation of hi's, till h 2 to the power n minus 1 divided by summation of hi's. And we know the summation of hi's means total number of pixels. So this is the definition of the probability, right? The probability of the occurrences. So here we calculate them and we get these numbers. We calculate them, we get these numbers. Do we know how many pixels have the value of intensity value of 1? By looking at this graph, can you tell me how many pixels have the intensity value 1? Shuma?
We don't because we don't know the size of the image.
Exactly. We don't because we don't know what is the original size of the image. If we knew, we just multiply with this number and we get it. But we don't. What will happen if I add all these numbers?
1.
I will get 1 because it is the probability distribution of the image. So if I add all the probability values, I get number 1. So, what we do, we come here and this time we are saying that, look, some of the pixels have high probability of appearance, some of them has low probability of appearance. So, as we stated before, those which are high probable, we call them very important, we call them cool guys, and we give them less number of bits. Those which are like hardly happening, we give them bigger numbers. Now, what happens here in this example, we gave the first three ones, only 2 pixels, 2 bits to represent. We say that we call 0.2501. We call the pixel which had this probability, in other words, intensity number 2, we call it 10, and intensity 0, we call it 11. Previously, when everything was equal, we were simply showing the binary numbers. 0 is 00, 1 is 001. This time, these numbers are not indicating, if you look at it, this is number 2, we know that, right? But it is representing 0. So, this binary number is not representing the number that it shows in decimal, but it's like a label that we are assigning to 0, or label that we are assigning to 1. And then we continue by giving 3 bits, 4 bits, and 5 bits, and so on. Now, let's calculate the average bit. We know that if we calculate the average bit here, we will get number 3. And if we want to calculate the average bit, what we have to do, we have here 2 bits, so we multiply 2 by this probability. Plus, here for example, we have 6 bits multiplied by the probability. We do this multiplication, we add it, and we get this number. Previously, for everything equal, we got 3, and for the new one, we get 2.7 bits. 2.7 bits. In other words, if I had 1 million pixel, I need to have 3 million bits. Here I need 2,700,000 bits. In other words, 300,000 bits have been redundant. I don't need them anymore. So you see, we are counting about 300,000. If every bit is 1 cent, so it means that like 7,000 euro has been saved, right? So it's big. I mean, the effect is very big. So this gives us this idea that, okay, if I am representing with different number of bits, I can compress. And the logic is this: high probable one should have less number of bits. Now, question which with high probability you are asking yourself, how do you know these numbers? So we want to talk about a method which gives us what are these numbers. Why this one has 2 bits, not 1 bit. And if it is 2 bits, why it is 0, 1, not 1, 0. So we want to talk about a very special, very famous technique, which is called Huffman coding, which you give these probabilities and it tells you that what are these numbers. But before we talk about that, let's proceed in order to understand and digest the concept. So in our example, as you can see, it tells us that we have about 10% of redundancy. We have about 10% of the redundancy for our example in our hand. In short, what we are doing is this. The highly probable bits will get the less number of bit allocation because they will happen more, so I can give them like, I give the example, I give him a 1-digit number instead of 2-digit number because it will happen more. And the ones which are less probable, I can give the higher number of bits because although it's higher, it's 6 bits instead of 3 bits, but it will happen only once or twice, so it doesn't really matter, right? So this is how the whole logic works. If your probability is high, the number of bits that you get should be lower. This is called, in general, coding redundancy. And we will talk about Huffman coding, which is a coding redundancy, in order to find out how we want to find those values. Now, tell me, is it a lossy method or is it lossless method?
Lossless.
It's lossless because although we give them different weight, I can construct everything back without any loss. Now, another method is called the interpixel redundancy. Interpixel redundancy means this. The example that I gave you with this pattern. Because so many of bits are zeros and ones, I don't need to tell you that 0, 0, 0, 0, 0, 0. I can tell you that, like in English, if you want to say a number, your bank account number, you don't say that 2, 2, 0, 0, 0, 0, 0, 0. You say that 2, 2, 5 zeros, right? Because it's shorter, and I understand that I have to put 5 zeros. The interpixel redundancy says this. If for a long period you have the same value, you don't need to repeat it. Tell me the value and tell me how many times. So it means instead of having a long 0, 0, zeros, I can tell you that 5 zeros. Right? So you have only number 5 and number 0 instead of having 5 zeros. So it will be much shorter. And the very best exaggerated example was this. Instead of having 1 million bits, we managed to have it by about 40 bits. So it's amazing. Interpixel redundancy will become very much meaningful in binary type of images. Here you see an image from a circuit, and this is, as you can see, a binary image. In other words, there are lots of zeros or ones happening. Remember, if 0 and 1 is happening frequently, like 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and there is no pattern like